Welcome back to another fascinating journey into the world of industrial manufacturing. Today, we're taking you inside PT Artas Energi Petrogas, one of Indonesia's premier seamless steel pipe manufacturers, where centuries-old metalworking principles meet cutting-edge technology. Seamless pipe manufacturing is a remarkable process that produces pipes without any welded seams, making them stronger and more reliable for high-pressure applications in oil, gas, and power generation industries. PT Artas uses what's called the Mannesmann piercing process, named after the German Mannesmann brothers who revolutionized pipe making back in the 1880s. It's amazing how some fundamental manufacturing methods stand the test of time. The journey begins with solid steel billets, cylindrical pieces of steel that typically measure about 12 inches in diameter and up to 30 feet long. These billets arrive at the facility, weighing several tons each. The first critical step involves heating these massive steel pieces in a rotary hearth furnace that reaches temperatures exceeding 2,200 degrees Fahrenheit. This isn't just about making the steel hot, it's about achieving uniform temperature throughout the entire billet, which takes approximately 2 to 3 hours. The furnace rotates slowly, ensuring every inch of steel reaches the precise temperature needed for the next stage. Once heated to that cherry red glow that old-time steelworkers knew so well, the billet moves to the piercing mill, the heart of this operation. Here's where the magic happens. The billet is fed between two massive rotating rolls set at an angle, while a piercing mandrel, essentially a bullet-shaped plug made of heat-resistant steel, pushes into the center of the rotating billet. As the rolls spin the billet and force it forward, the mandrel creates a hole right through the center. The physics here are fascinating. The rotational force and the geometry of the rolls create stresses that actually help open up the center of the solid steel. It's controlled metallurgical violence that turns solid steel into a thick-walled hollow shell called a bloom. This bloom then proceeds to the plug mill section, where it passes over another mandrel while being worked by additional sets of rolls. Think of it like rolling out dough, except this dough is glowing steel at nearly 2,000 degrees. The plug mill elongates the bloom and reduces the wall thickness, transforming that short, thick-walled piece into something longer and closer to the final pipe dimensions. Multiple stands of rolls work in sequence, each progressively refining the shape. Next comes the reeling mill, where the pipe receives further elongation and wall reduction. This equipment uses a mandrel bar that runs through the entire length of the pipe while rolls work the outside. The precision here is remarkable. The machinery controls wall thickness to tolerances of just a few hundredths of an inch on pipes that might be 30 feet long and several inches in diameter. Modern computer systems monitor every aspect, but the fundamental process would be recognizable to metallurgists from 50 years ago. After this hot forming process, the pipe enters a stretch-reducing mill, a series of stands, sometimes 40 or more, that gradually reduce the outside diameter while the pipe is still hot but cooling. Each stand has grooved rolls that work the pipe slightly smaller. The pipe travels through at impressive speeds, sometimes over 20 feet per second, with cooling water sprays between stands controlling the temperature profile. The pipe then moves to the cooling bed, a long section where pipes are laid out to cool uniformly. Proper cooling is crucial because it affects the pipe's metallurgical properties and prevents warping. Once cooled, each pipe goes through cold finishing operations. This includes straightening, where massive hydraulic presses correct any bends or curves. The straightening machine uses precision measurements and applies pressure at specific points, much like an experienced craftsman would, but with computer-controlled accuracy. Quality control at PT Artas involves multiple inspection stages. Ultrasonic testing equipment sends sound waves through the pipe wall, detecting any internal flaws invisible to the eye. Eddy current testing checks for surface defects. Hydrostatic testing fills pipes with water and pressurizes them well beyond their working pressure to verify integrity. Each pipe also receives dimensional inspections, checking diameter, wall thickness, and length against specifications. Finally, the pipes are cut to precise lengths, beveled at the ends for welding, and marked with identification codes before shipping. This comprehensive process ensures every pipe leaving the facility meets international standards for the demanding applications they'll serve in oil fields, refineries, and power plants worldwide. Now let's travel to Germany and step inside Metall Gießerei Mannheim, or MGM, a facility that keeps alive one of humanity's oldest manufacturing arts while embracing modern precision. Metal casting and pattern making represent traditions that date back thousands of years, and there's something deeply satisfying about watching molten metal transform into useful components. The pattern making process starts with engineering drawings that specify every dimension of the final part. Computer-aided design software helps translate these drawings into three-dimensional models. The CNC machines then mill these patterns, their cutting heads dancing across the material with movements controlled to thousandths of an inch. For complex shapes requiring cores, internal passages within the casting, separate core boxes are also created. Once patterns are complete, they move to the molding department. MGM uses several molding methods depending on part size and production volume. For larger castings, they employ greensand molding, a process that would be familiar to foundrymen from a century ago. The molding sand, a mixture of silica sand, clay, and water, gets packed around the pattern in a flask, a metal frame that contains the sand. The pattern is then carefully removed, leaving a cavity that perfectly replicates its shape. For more intricate parts requiring finer detail, MGM uses resin-bonded sand systems. Here, sand mixed with chemical binders gets blown into a core box under pressure, creating cores that are then cured, either by heat or chemical reaction, into rigid forms. These cores can create complex internal geometries that would be impossible to achieve otherwise. After cooling, which can take hours for large castings, the molds are broken open in the shakeout area. Vibrating tables help separate the casting from the sand, which is then reclaimed and recycled for future molds. The rough castings move to finishing operations, where gates and risers, the extra metal that aided the pouring process, are cut away. Grinding removes any surface imperfections, and shot blasting cleans the surface. Finally, each casting undergoes inspection and testing before shipment. It's this combination of ancient art and modern precision that makes MGM a leader in their field. From Germany, we're heading to the United States to witness something truly extraordinary: rocket manufacturing at United Launch Alliance's massive facility. For those of us who watched the space race unfold in the 60s, seeing how rockets are built today is like witnessing science fiction become reality. The manufacturing process begins with the rocket's structural components, primarily made from aerospace-grade aluminum alloys. These aren't your everyday metals. They're specially formulated to provide maximum strength while minimizing weight, crucial when every pound matters in spaceflight. Large sections arrive at the facility as machined aluminum panels and rings, some measuring over 17 feet in diameter. In the welding bay, skilled technicians use friction stir welding, a solid-state process invented by the Welding Institute in Cambridge, England in 1991. Unlike traditional welding that melts metal, friction stir welding uses a rotating tool that generates heat through friction, plasticizing the metal and joining pieces together without melting. This creates exceptionally strong, defect-free welds critical for containing the extreme pressures and temperatures rockets experience during launch. The assembly area resembles a high-tech cathedral, with overhead cranes capable of lifting sections weighing tens of thousands of pounds. Workers in clean room suits assemble the rocket stages vertically, stacking them with precision measured in fractions of an inch. Each stage contains intricate plumbing systems for fuel and oxidizer, miles of wiring for instrumentation and control systems, and structural supports designed to withstand the violent forces of launch. The propulsion systems represent some of the most sophisticated engineering on Earth. The RD-180 engine used on Atlas V rockets generates over 800,000 pounds of thrust, burning refined kerosene and liquid oxygen. These engines arrive from Russia as complete units, a fascinating example of international cooperation that began after the Cold War ended. Each engine undergoes extensive testing and integration with the rocket's fuel systems, a process requiring meticulous attention to every connection, seal, and valve. The final assembly includes installing the payload fairing, the protective nose cone that shields satellites during ascent through the atmosphere. These fairings are composite structures, made from layers of carbon fiber that provide strength and thermal protection while remaining lightweight. The interior is lined with acoustic dampening material because the sound generated during launch can reach levels that would damage sensitive satellite electronics. Before shipping to the launch site, each rocket undergoes a final comprehensive review where engineers verify every system, every component, every measurement against specifications. It's this dedication to perfection that has made ULA one of the most reliable launch providers in history, with a success rate exceeding 98%. Watching these magnificent machines come together reminds us that American manufacturing, when it needs to achieve the impossible, still leads the world. Let's shift gears now to look at something that might seem mundane compared to rockets, but is equally essential to modern industry: hydraulic and pneumatic cylinders. Everest Canto Cylinder, a global leader in cylinder manufacturing, shows us how these workhorses of automation and machinery come to life. Cylinders are the muscle of countless machines, from construction equipment to factory automation systems. The manufacturing process begins with steel tubing called barrel stock. This seamless tubing arrives in long sections and gets cut to precise lengths using automated saw systems with carbide-tipped blades. Each barrel section then moves to the honing department, where the magic of precision happens. Honing machines use abrasive stones mounted on expanding mandrels that rotate inside the cylinder bore. This process removes microscopic amounts of material, creating a surface finish so smooth it looks like glass. Meanwhile, piston rods are manufactured from high-strength steel bar stock. These rods get turned on CNC lathes that machine them to precise diameters, then move to induction hardening equipment. After hardening, the rods receive chrome plating, an electrochemical process that deposits a thin layer of chromium onto the surface. This chrome layer provides exceptional corrosion resistance and an ultra-smooth surface that extends seal life. Each finished cylinder leaves the facility ready to push, pull, or lift loads for years of reliable service in the demanding applications they're designed for. Now we're heading to Serbia to witness something that connects us directly to history: the manufacturing of artillery shells at the Kovac Center in Valjevo. This facility, sponsored by Jugo Import SDPR with infrastructure provided by Krusik, represents a manufacturing tradition that stretches back through both world wars and beyond. For those of us who remember the industrial mobilization that characterized the 20th century, this process carries particular resonance. Artillery ammunition manufacturing combines precision metalworking with pyrotechnic science, and every step requires absolute attention to safety and quality. The process begins with raw steel billets, solid cylinders of carefully formulated steel alloy. The steel composition matters tremendously here. It must be strong enough to withstand the explosive forces during firing, but not so brittle that it shatters unpredictably. These billets enter hot forging presses, massive machines that can exert thousands of tons of force. The steel is first heated in induction furnaces to approximately 2,000 degrees Fahrenheit, making it plastic enough to deform under pressure. The glowing billet is then positioned in a die, and the press closes with tremendous force, squeezing the steel into the basic shape of the shell body. This hot forging process aligns the metal's grain structure, creating superior strength compared to machining from solid stock or casting. The forged shell bodies, called blanks, move through a series of machining operations. CNC lathes turn the exterior to precise dimensions, creating the ogive, the curved nose section, and the cylindrical body with its distinctive driving band groove. This driving band, a ring of softer metal like copper that gets installed later, engages the rifling in the artillery barrel, spinning the shell for stability in flight. The precision required here is remarkable. The diameter must match the gun barrel within thousandths of an inch, and the ogive shape affects ballistic performance. Inside machining is equally critical. The shell body gets bored out to create the cavity that will hold the explosive charge. The wall thickness must be uniform and calculated precisely. Too thin, and the shell might burst prematurely. Too thick, and the fragmentation pattern won't be effective. Engineers use complex calculations based on the explosive type, desired fragmentation size, and target effects to determine these specifications. Threading operations cut the base threads where the fuzz will screw in, and the nose threads for shells that use point-detonating fuzzes. Thread quality is critical because these joints must seal reliably and withstand extreme forces. The fuzz, the cavity inside the nose, receives special attention during machining because the fuzz components fit here with precise tolerances. After machining, each shell undergoes heat treatment. They're placed in large furnaces and heated to specific temperatures, then cooled in controlled ways to achieve the desired hardness and toughness balance. This heat treatment process, developed through decades of metallurgical research, ensures the shell will perform reliably under the extreme stresses of firing and impact. Quality inspection at this stage is exhaustive. Magnetic particle inspection reveals any surface cracks. Ultrasonic testing checks for internal flaws. Dimensional inspection verifies every critical measurement. Any shell failing these inspections gets scrapped. There's no room for defects in munitions manufacturing. The driving band installation comes next. These copper bands are machined slightly oversized, then pressed onto the shell body using hydraulic presses. The interference fit, where the band's inner diameter is slightly smaller than the shell's outer diameter, creates a permanent mechanical bond. When the shell is fired, this band engraves into the gun's rifling grooves, imparting the spin that stabilizes the projectile in flight. Painting follows a specific protocol. Shells receive multiple coats that identify their type, explosive fill, and manufacturing date through a color coding system standardized internationally. This isn't decorative. It's critical identification that allows ammunition handlers to select the correct munition for their mission, even in battlefield conditions. The explosive filling process happens in separate, specially designed facilities with extensive safety measures. The shell bodies are carefully filled with explosive compounds like TNT, Composition B, or modern insensitive munitions that are safer to handle and store. The filling process must eliminate any voids or air pockets that could cause unpredictable detonation. For some shell types, the explosive is poured as a molten liquid that solidifies as it cools. Others use pressed explosive pellets. Fuzz installation completes the assembly. Artillery fuzzes are sophisticated devices that might include time delay mechanisms, impact sensors, or proximity detection electronics. Modern artillery shells can be set to detonate at specific points in their trajectory, burst above targets, or penetrate before exploding. The fuse threads into the shell base with a specific torque applied by calibrated wrenches, and a safety wire often secures it. Final inspection includes weighing each complete round, checking fuse installation, verifying paint coating, and visual inspection for any defects. Samples from each production batch undergo actual firing tests to verify performance meets specifications. This destructive testing ensures the entire batch performs as designed. The finished ammunition receives careful packaging in sealed containers, with desiccant to control moisture, then labeling with lot numbers that allow every round to be traced back to its specific production date and batch. This traceability is crucial for quality control and safety recalls if any issues emerge. The manufacturing of artillery ammunition at Kovac Center represents the intersection of traditional forging techniques, modern CNC precision, and stringent quality control that ensures reliable performance when these shells are needed. It's a sobering reminder of the industrial capabilities that nations maintain for defense purposes, built on manufacturing expertise refined over more than a century of arms production. For our final segment, let's explore something that will resonate with anyone who's ever watched heavy equipment shape the landscape. Bulldozer manufacturing at Crosland Technica's facility, where they produce the Dresda line of heavy equipment. There's something quintessentially American about a bulldozer, even though we're looking at modern international manufacturing. Manufacturing a bulldozer is like building a bridge that moves. The process begins with the undercarriage, the tracked running gear that gives these machines their incredible traction and ground pressure distribution. The track frames are welded structures made from thick steel plate, cut on CNC plasma tables that use superheated ionized gas to slice through steel several inches thick. Watching these machines work is mesmerizing. The plasma torch moves with computer-guided precision, cutting complex shapes that would have required hours of manual labor in earlier eras. These cut plates move to welding stations, where certified welders join them, using both robotic and manual welding techniques. The frames must withstand enormous stresses, supporting machines weighing 40 to 70 tons while traversing rough terrain. The welding procedures are specified in detail, controlling heat input, pass sequence, and inspection requirements. X-ray inspection verifies critical welds, ensuring no hidden defects compromise structural integrity. The track rollers, components that support the tracks and guide them around the frame, are precision machined from cast steel. These rollers spin on sealed bearing assemblies that must survive incredibly harsh conditions: shock loads, abrasive dirt, extreme temperatures, and moisture. Each roller gets assembled in climate-controlled areas, where cleanliness prevents contaminants from entering the bearing seals. The seals themselves represent sophisticated engineering, often featuring multiple lips and spring-loaded elements that maintain contact pressure despite wear. Track shoes, the individual segments that link together to form the endless track, arrive as castings from specialized foundries. These grouser shoes, named for the raised grousers or cleats that provide traction, can weigh over 100 pounds each. They're heat-treated for hardness, then machined on the mounting surfaces where they connect to track links. The track links themselves are forged steel components that connect the shoes into a flexible chain. Pins and bushings, precision ground to exact diameters, join these links together. When properly assembled and maintained, these track systems can operate for thousands of hours before requiring replacement. The main frame assembly forms the machine's backbone. This massive welded structure, fabricated from steel plates and structural sections, provides mounting points for the engine, transmission, final drives, and all other major components. Building this frame requires extensive fixturing, specialized jigs and frames that hold components in precise positions during welding. Modern laser alignment systems verify positions before welders make permanent joints. The transmission and torque converter installation follows. These powertrains convert the engine's rotational power into the slow, powerful motion needed for dozing work. The torque converter acts like an automatic clutch, multiplying torque at low speeds and providing smooth power delivery. The transmission, often a powershift design with multiple forward and reverse gears, allows the operator to select the appropriate speed for the task without stopping. Final drives, the gear reduction units at each track, mount to the mainframe and receive the transmission's output. Inside these housings, planetary gear sets provide additional torque multiplication, while allowing the sprockets, the toothed wheels that drive the tracks, to rotate at the optimal speed. These final drives are assembled in clean rooms because even microscopic contaminants can cause premature gear wear. The operator's cab installation represents the final major assembly step. These ROPS-certified rollover protective structures meet stringent safety standards using heavy-gauge steel construction and safety glass. Inside, ergonomic seats with suspension systems isolate the operator from machine vibration. Joystick controls or traditional lever systems, depending on model and customer preference, allow precise control of all functions. The electrical system ties everything together. Modern bulldozers contain sophisticated electronics monitoring engine performance, transmission operation, hydraulic pressure and temperature, and providing diagnostic capabilities. Wiring harnesses, pre-assembled on special boards to ensure correct routing and connector engagement, snake throughout the machine. The electrical system also powers lights, the starting system, and increasingly GPS-based grade control systems that can automatically control blade height to match pre-programmed terrain designs. Before leaving the factory, each machine undergoes comprehensive testing. Technicians verify all systems operate correctly, checking hydraulic pressures, testing electrical circuits, and running the engine through various loads and speeds. The machine then moves to a test pad where operators run it through its full range of motion, cycling every hydraulic function, testing steering response, and verifying track operation. Any issues discovered result in immediate correction and retesting. Finally, each Dresta bulldozer receives a thorough cleaning, protective coatings on exposed metal, and detailed preparation for shipping. These magnificent machines, representing hundreds of hours of skilled labor and engineering excellence, head out to construction sites, mines, and industrial facilities worldwide, ready to reshape the Earth for another generation of development. That's the enduring legacy of heavy equipment manufacturing, building tomorrow with lessons learned yesterday.